Hello, everyone. We're going to get rolling here. So the plan tonight is we're going to begin looking at ideas within Chapter 4. Chapter 4 is considering reactions that take place in aqueous solutions. The word aqueous there, that's referring to in water. So almost all of the chemistry that we look at that's taking place in a solution in this course takes place in water, which makes sense. Such a large proportion of our planet is water, and so much interesting chemistry takes place there. Um, that doesn't mean that water is the only spot that you could have solutions. In a lot of organic chemistry, they look at other solvents besides water. But within this course, water is going to be our main focus. Within the chapter, a lot of different chemistry ideas here. This one we're going to spend a little bit more than 1 week on, chapter 4. So we'll be exploring ideas Tuesday and Thursday, and then next Tuesday is when I think we'll wrap up the chapter. So this is one that takes a little bit longer, a lot of different ideas. This evening, we're going to look at a few general properties of aqueous solutions, and we want to be able to apply terms like strong and weak electrolytes, non-electrolyte, and thinking about those in different ways, maybe a particle representation or how it's connected to conductivity measurements. Then what we're going to do is we're going to spend some time looking at oxidation reduction reactions. I shifted this a little bit compared to what's in the textbook. The textbook does oxidation reduction reactions about 2/3 of the way through, but I think it's going to be a good match for us as far as how we spend our time this evening. So if you look in the textbook and you see that it's a little different order, I'm aware of that. So the general plan here, we had a pre-class video that really helped me to learn your perspective and your views on different things, what your initial understanding is. What we're going to do initially is we're going to look at characteristics here of these aqueous solutions and what happens when we add something to the water. And that something we're going to describe as being a solute that could be a strong electrolyte, a non-electrolyte, or this in between, a weak electrolyte. And we want to think about that in terms of what's taking place at the particle level and how we represent it. That idea then sets us up for really the rest of the chapter. So the idea is that let's first of all think about how something dissolves in water, and then we're going to connect it to different types of reactions that can take place. Now, these different types of reactions, all of these are big ideas in the second semester in 1220. Ideas, a lot is spent looking at acids and bases, different kinds of precipitation reactions, titrations. So my point is a lot of the really good questions that people had, I saw within Peruzzo before class, some of those are deeper questions than we're going to have to get to. They're ones that would be answered best in the second semester. So I really like the way you're thinking about it. I'm just pointing out that chapter 4 is sort of a preview for those. This idea of how does a compound dissolve in water, I think about it as before we look at the types of the reactions, we have to ask, well, what's in the beaker? And when I say what's in the beaker, what particles are in the beaker? We could write a formula for it, but what are going to be present within the beaker that could potentially react in these different ways? That's how I think about the parts. So when I stack up and I look at the different ideas and skills and what we need to do within chapter 4, there's a lot of different ideas and skills, but I think you're going to do well with them. The first idea of looking at the characteristics of these aqueous solutions, I put that in the category of can we make predictions for what are going to be strong, weak, and non-electrolytes. So that's where we're going to start class. And then we're going to look at this idea of oxidation reduction reactions. And we have 3 distinct skills that fit together there. Assigning oxidation numbers, using them to analyze redox reactions. Redox stands for the reduction and oxidation. We'll look at that tonight. And then making predictions involving the activity series. Even though I put that at the top as far as one of the more challenging ideas, I don't think it needs to be. I think with a little time, that's actually going to be an easier one than is historically the case. So let's see if we can accomplish that. So on this slide right here in section 4.1, there's various general properties for this aqueous solutions. And there's classifications being made of causing things non-electrolytes, weak electrolytes, and strong electrolytes. This particular slide right here, I'm going to keep coming back to it and fill in more and more information. So this is sort of going to be like a summary slide. An initial thought is when we're looking at these definitions for non-weak and electrolytes, a non-electrolyte is if you add a solute to the solvent, you would have molecules present. So we've got a couple terms there. A solution is a mixture of more than one component. The component that is present in the largest amount, the greatest proportion, that's called the solvent. So in our cases, water is the solvent. Most of our beaker is filled up with water. We're adding something to it. The thing that we're adding in a smaller proportion is called the solute. So if you add the solute to the water, to the solvent, if the thing that you are adding remains as molecules, we call that a non-electrolyte. A weak electrolyte would be mostly molecules, but you might have some ions present as well. In a strong electrolyte, we have ions present when it dissolves and we don't see any molecules there. So these would be our general initial classifications. Now we have a way to test whether something is an electrolyte or not. We can use what's called a free ion detector. We've got a probe that when it goes into the water, if there are ions there free to move about, the light bulb goes on. This would be called a conductivity probe. We don't really have to worry about the mechanism for how it's working, but we can just know that when the light bulb goes on with a conductivity probe, it's telling us that we have free ions in the solution. Now, if we're exploring this, let's classify a few things and see if we can come up with some generalizations. So let's look at water, sugar, and sodium chloride. And when I say look at these, let's look at them within this PhET sim called sugar and salt solutions. If you want to play with it, you can go to the PhET website. I think it's a helpful one. I had fun exploring it, and that's what I shared within the first video. So here's one of the things that I set up within that. And again, I appreciate your comments and your analysis on that. When I tested a solution where it was just the water, the light bulb didn't go on. This is saying that there are no free ions within the water. We have water molecules, and we don't have the conductivity probe lighting up. Now, if we added the sugar to it, I didn't see the light bulb go on then either, but when I added the sodium chloride to it, the salt, the light bulb definitely went on, definitely produced free ions in solution. So this is what I mean when I say that we have a probe to say whether the thing that we add, does it remain as molecules or does it separate out to give us ions? So at the particle level, this is what I think would be taking place. So here I've got a whole bunch of water molecules. They'd be jiggling, moving around. They're remaining as molecules. I don't have free ions present. So that's why when I test the water itself, the light bulb doesn't go on. Now, when I add sugar molecules, I see the sugar molecules are separating apart. The sugar is beginning to dissolve, but it remains as a molecule. I'm not seeing any ions present. So that leads me to classify sugar, no free ions. I'd call it a non-electrolyte. Now, in contrast, if I add the sodium chloride to it, it's going to dissociate. It separates apart, and now it's separating apart, and I see I have distinct ions present that are free to move about. Light bulb goes on, so I would say my free ion detector, my conductivity probe, is telling me that sodium chloride, when it dissociates, it gives me ions. So if we were beginning then to classify these, I would say examples of non-electrolytes, H2O would be an example, as would the sugar. I would say the strong electrolyte, the example right here would be the sodium chloride. If I wanted to begin to symbolically say what's going on, I could start with the sugar as a solid. When I add it to the water, it becomes aqueous. That's what the AQ means. It means it's dissolved within the water. It doesn't mean it gives me ions. It just means that it has dissolved. This would be my representation for what happens when I'm adding the sugar and it's dissolving in the water. I could think about that as well with the salt, the sodium chloride. I could begin with salt. It becomes the sodium chloride aqueous. But now I need to think about this a little bit more deeply. When it says sodium chloride aqueous, what's in the beaker, what's in my head is, I don't have sodium chloride stuck together. I have it as the distinct ions that are present. There are no molecules present. Ions are produced when the sodium chloride is added. It began all stuck together as a solid and it's come apart to give me those ions. So my point here is that symbolism, sodium chloride aqueous, let's not be thinking molecules. Let's be thinking that this is telling us the interpretation of that would be these ions present. Now, within the PhET sim, we can also explore different things that we could add to it. So let me summarize that here. So we saw that when we added sodium chloride, we had sodium ions and chloride ions. Other things that you could explore within that, oops, sorry about that. You could see, what does calcium chloride aqueous look like? And the sodium nitrate aqueous. So as I'm looking within this, in each of these cases, it looks like, if I look on sort of the score sheet here where it's showing the concentration, it looks like in each of the examples, I'm seeing ions present. Each of these, I think I have free ions, and the conductivity probe would tell me that the light bulb goes on in each of the cases. Now, as I look within this one, the designers on this for sodium chloride, calcium chloride, sodium nitrate, they could have chosen anything within here. I know the designers within here, and I'm curious, why do you think these designers for the sim here, the software people, why did they choose these particular examples? Sodium chloride, calcium chloride, and sodium nitrate. What do you think their rationale was for that? They could have chosen different things. Why do you think they chose these? Tell me in the chat on this. Why do you think they chose these particular ones? So I'm seeing responses within here uh, describing how in each of these cases they are going to dissociate. But I think the designers of this, they chose these particular examples to try to illustrate something a little bit more more intentional than that. And by that, I mean, if I look at these examples, I like the observation that they're all ionic compounds. So one of the reasons I think these were included in the sim was they wanted to show us that ionic compounds are strong electrolytes, that when they're added to the water, they dissociate and they give us these ions. So I think that's one of the reasons that they chose these. They're all ionic compounds. Another thing though, if I look at the example, notice here, if I'm looking at the sodium chloride in the solid, they are in a 1-to-1 empirical ratio, in the empirical formula. And when they dissociate, they stay 1-to-1. I think the reason they chose the calcium chloride is they wanted to point out that, notice when it dissociates, it gives me the chloride ion. And in the empirical formula, there's one calcium and 2 chlorides present, and that shows up when it dissociates as well. And in this last example, I'm going to agree with Catherine's observation here. They chose a polyatomic anion because they wanted to demonstrate that the polyatomic anion stays together as the ion when it dissociates. I think that they were very intentional because they wanted to illustrate different things. They wanted to choose an example where the empirical formula is 1-to-1, and that's how it dissociates. An example where it's 1-to-2, and that's how it dissociates. And an example where it's 1-to-1, and one of the features is a polyatomic. I think that's why they chose this particular set. Another thing that I found within that sim, I could use different types of sugar. I could use sucrose, I could use glucose. In both of those examples, when I added it, I saw that the molecule itself was staying together. So I would say both of these examples, these are different types of sugar. These are both examples of non-electrolytes. Both of these are remaining as molecules. And if I look more closely, I'd say in both of these cases, these molecules are entirely nonmetals. I see elements carbon, hydrogen, oxygen. I think that might be a generalization that we're going to be able to make. I'll summarize that for us in just a second. But it sure seems different than if I compare what happens when I added sodium chloride. The sucrose, a sugar, is staying together as a molecule. In the ionic compound, the sodium chloride is breaking apart into the ions present, and that the free ion detector would tell me that. One more thought within as I look with that, this sort of score sheet here telling me what's in there, it's calling that the concentration. The concentration of solutions is something we'll look at in chapter 4. Now, I manipulated that a little bit. In one case, I added a lot more water to the container. And in the other case, I had the water evaporate off. In both of those, I kept the sugar and the sucrose the same amount in there. All I did was change the amount of water. And now, as I look at that, it looks like they had the concentration changed. When I added more water, the concentration went down. And when I removed the water through evaporation, the concentration went up. So that gives us a clue what the concentration is telling us. The concentration is describing the amount of the solute that I have relative to the amount of the solvent, the water. We could look at that in different ways. Maybe it's a ratio, maybe it's some other proportion. In this chapter, in chapter 4, we're going to discuss a unit for the concentration called the molarity. But what right now, I think we have a picture of the concentration is telling us something about the amount of the solute there relative to the amount of the solvent. So if we change the amount of water that was present, that was changing the corresponding concentration. So if I go back to this and add a few more details. So when I'm thinking about strong electrolytes, sodium chloride was a strong electrolyte, gave me ions. How about magnesium chloride or potassium sulfate? These are all ionic compounds. I think we have a pattern here. It sure seems like all the ionic compounds are strong electrolytes. So when I think about magnesium chloride, if I say magnesium chloride aqueous, I've dissolved it in water. I have to think, okay, what is that aqueous telling me? It's telling me that it has broken apart into the corresponding ions. Magnesium 2 plus and 2 of the chlorides that are there. That's how I'm interpreting what happens with magnesium chloride aqueous. Take a second. What would you predict happened with the potassium sulfate? What does potassium sulfate aqueous represent? I'm thinking it's an ionic compound. I'm thinking that like other ionic compounds, I can describe it as being aqueous, but what's really going on is it's dissociating and giving me the corresponding ions. So it's dissociating and giving me potassium ions. I would have 2 of those, and the sulfate polyatomic anion. The idea of aqueous just means that the solute has dissolved, but it doesn't tell me if it remains together as an ion or as a molecule. I could talk about sugar aqueous, it stays a molecule. I could talk about sodium chloride aqueous, and the aqueous part, I have to be thinking, what does it mean when I have an ionic compound aqueous? It means that it's telling me I have the ions present. This is my distinction here between something being a non-electrolyte and a strong electrolyte. Now, if I were to think of other examples of non-electrolytes, right now I would say, okay, there are going to be other molecular compounds. Methanol, that is a discrete molecule. I'm going to say that that is a non-electrolyte too. When I add it to water, I think it stays together as the methanol when it dissolves. Even a gas, something like methane, CH4, it can dissolve. And I'm thinking, okay, given the pattern that we've seen so far, I think it's going to stay together as those particular methane molecules. So right now, we're going to continue to add details on it, but let's have this be our initial understanding. Non-electrolytes are when we have molecules present. And it sure seems like these molecular compounds are examples of that. Strong electrolytes, Those are occurring when we have ionic compounds. And with those, we have to be extra careful to consider how does it dissociate and break apart to give us the ions in solution. I'm skipping over the example right here for weak electrolytes, because right now we don't have any examples of those. We'll add to it. We talk about them certainly within chapter 4, but right now let's just have our division between non-electrolytes and strong electrolytes. So one way I've seen this on tests and explored with different particle representations. So within this one, take a second here, see if you can assign these. And by assign these, does A best represent a strong, weak, or non-electrolyte? How about B, C, D? So take a second. I'll share my answers with you in just a moment, but see if you can apply that terminology to these particle representations. What I'm looking for is, do I have only ions present, only molecules present, or do I have a combination? So if I'm doing within my analysis here, I think this would be my best description. I see a strong electrolyte, a non-electrolyte, a weak, and then another strong. So what I'd like you to do within this one, this was my work right here. Tell me, do you find any of these confusing? Are there's any of these that you want more information on? A, B, C, D. Any of these that you find confusing? The idea here on C, if you're going to say, well, I don't really get one, I would be agreeing with you. Because with C, we haven't seen any examples yet. Okay, we've seen what does it mean to say it remains together as a molecule? That would be a non-electrolyte. It breaks apart into the corresponding ions. That would be a strong electrolyte. With C right here, we've got a combination. So within a combination, I haven't really given you any examples of that yet. That's something that we'll add to our skill set come Thursday. Now, if I look more closely here, and we have a comment here being made about the different ones, the idea of, it says in A and D, which of these would be stronger? We have two examples, I agree, of A and D. Both I'm describing as strong electrolytes. What do you see different though between A and D? In both cases, I have all ions. What do you think that the authors would try to be drawing your attention to within A and D? Both cases that are entirely ions present. And what I'm seeing in your response is I agree within this. It seems like they're also trying to draw our attention to the charge. If I look more closely on the one at the left, it looks like that this would be coming from an ionic compound that had +1 cations and -2 anions. Because I see that I have +1 cations and then the 2- for the anions. The overall charge ends up being 0, as it should, because it would have started out that way in the empirical compound. The comment here is, or the question, is there a degree of strength within these? We can look at that a little bit more when we talk about concentration, but right now in our classification scheme, if something only gives me ions, we're going to call that strong. We're not going to say extra strong, super strong. A strong electrolyte is something that only gives me ions. It doesn't matter if they break apart 1-to-1 or in this 2-to-1 ratio. Our definition of strong is simply going to be we've got ions present. And on the other extreme, we don't have any ions present. That would be our non-electrolyte. Okay, so it seems like folks are doing a good job within our analysis here. When I look end of chapter, the kinds of things that you're being asked to do with this. So I see different pictorial representations. One of these on the left, 4.1, is asking, which of these would be most consistent with lithium sulfate? So we've got to consider classifying that. Do we predict it to be strong, weak, or non-electrolyte? And then looking more closely at the charges, that would be an example. 4.2, this is very similar to what we were just doing of assigning things as strong, weak, and non-electrolytes. So one style of question is related to these particle pictures. Here's another question that I saw that were paired up. This is saying, tell me which ions are present when you add these particular solutes to water. So in each of these cases, if I were to look at these, what they're asking is, how does this dissociate? When I'm looking within the list, I see a lot of ionic compounds. I see iron 2 chloride. I see ammonium sulfate. I see calcium hydroxide, magnesium iodide, potassium carbonate, sodium acetate. So I have a lot of examples of ionic compounds, and it sure looks like they want me to recognize that I need to keep the polyatomic anions and polyatomic cations together. And I think I can do that. One additional thing I see within this, though, they're listing nitric acid as something that produces ions. And they're saying HClO4, that's another acid that they're saying produces ions. Let's put that idea on hold a little bit. I think we need to know more in this chapter about how the acids are producing ions. Because after all, something like nitric acid, those are entirely nonmetals. That's not an ionic compound. That's a molecular compound. So we're going to have to figure out how to classify acids within our scheme right now. But initially, I think that we can look at molecular compounds in general and see how they're non-electrolytes. And I think we've got a lot of ability to be able to classify ionic compounds. In our next class, we'll expand a little bit and see where acids fit within our description. Because something must be going on, because it tells me that those produce ions too. So that's the start. That's 4.1, getting us a sense of this category for me of what's in the beaker. Now, we have one type of reaction that we're going to look at that can take place with these things in aqueous solutions, or they take place actually other times as well. And that's what are called redox reactions. So within here, we've got three really clear skills that we want to be able to have that build on each other. The very first skill is we need to be able to assign oxidation numbers. We'll practice that in just a second. We use those when we interpret redox reactions. And then from that, we're going to then connect that to what's called the activity series. So let me then go through this part. So when we're talking about, if I use the phrase redox reactions or oxidation reduction, I'm really just combining these two words. Oxidation reduction, when it's called redox, that's the reduction oxidation. I'm just switching it around the other way. So within here, here's a picture for what would be taking place. This is an example of an oxidation reduction reaction that turns out is not taking place in water. The example here is when you take calcium solid, it reacts with oxygen gas to form calcium oxide, this ionic compound. If we look more closely within the picture here, this E minus, they're trying to say that an electron is leaving the calcium and going to the O2 molecule. An electron is being transferred in the process here. The electron is leaving one of the substances and going to the other one. So when we're doing oxidation and reduction reactions, we're interested in the transfer of electrons. The substance that is identified as being oxidized, that is losing an electron, or more than one electron. The one that is gaining the electron is being called and identified as reduced. There's different ways, mnemonics that I've seen. A lot of times I've seen this oil rig where oxidation is losing the electron, reduction is gaining. So we want to know this terminology for oxidized and reduced. Oxidized means losing electron. When it's reduced, it's gaining electron. Now, in order to make sense of these reactions and determining whether something is gaining or losing electrons, we need to have like a numbering scheme to do this. We need to first identify what are called the oxidation numbers for the different atoms that are present. And with that information, we can track through and determine whether something is gaining or losing electrons. So our first step that we have within here begins with assigning oxidation numbers. So the general idea with oxidation numbers is if you have different types of atoms and they don't share the electrons in the compound, what would their charge be? That's the question we're asking with oxidation numbers. So I'm curious, when it comes to oxidation numbers, what's your prior knowledge on this? I'll send you a poll on this. Are you a 1, 2, 3, or 4? Never saw it, or you're starting from 0? Vaguely remember it? You feel like you're pretty good, or you'd say you're very good? Take about 10 more seconds. So to show you where you're at with relative to your classmates within here, if you say that you're not really strong at this, if you're starting out at a 1 or a 2, you're not alone within our group. I know that this is an essential skill that we're going to need to build and do other tasks within the chapter. So this is something that within the recitations this week, I definitely want the teaching assistants to focus on to help improve this for you. The when we're doing this task of assigning oxidation numbers, let me add a different idea for us. It's this idea that when you have different atoms within a compound, the electrons are more frequently going to be found on what I'm going to call the more electronegative atom. Okay? The more electronegative atom is the one that is more strongly attracting the electrons. Now, the most electronegative atom is fluorine. When it is found in compounds, it's the one that is most attracting the electrons within the compound. There's also, I would say, if you look at the periodic table, a real clear trend for electronegativity among these nonmetals. We don't worry about the noble gases because they're not found in compounds, but we see that we have these trends where as we move towards fluorine, the electronegativity goes up. So fluorine would be the one most prone to become negative. What would be sort of the second tier? Well, the ones right next to it, like oxygen and chlorine. So we have a really clear pattern for how things attract electrons when they're in compounds. Now, I'm bringing this up. This is an idea that we actually get in chapter 7, but I think that it's helpful of sort of knowing this pattern when we're doing these particular assignments. So I'm curious, I brought up electronegativity. Help me out on this one. Is this something, what's your skill on this one? Have you heard this before? You're good at it. Where do you find on this concept of electronegativity? Take about 10 more seconds. So this is a particular idea. Like I said, we're going to discuss it quite a bit more later on, about halfway through the semester here. But I think that it's a useful sort of guideline for us because I find that it's a very helpful connection when we're trying to make sense of assigning oxidation numbers. When the idea of oxidation numbers show up in chapter 4 here, it's sort of like, well, here's just some rules. But for me, it's helpful to understand when I'm looking at these nonmetals, just the pattern on the periodic table, that helps me understand within my assignments. Let me show you what I mean here. So first of all, here's the question: determine the oxidation of sulfur in each of these different substances. So one observation within here, the oxidation number of sulfur must be able to change. because I'm being asked to assign what it would be in these different substances. So we're going to need a strategy to be able to determine what would be sulfur in these different examples. Now, what we're going to find is we're going to have to memorize, I think, a little bit, but we also need a problem solving approach. We can't just memorize every single compound. We must do more than memorize. We sort of need a plan. So let me step you through what is a plan that will allow us to get the oxidation number for any atom in any compound. So first of all, I'm going to look to the textbook here because I think the textbook does a pretty good job explaining this. So it brings up the idea of oxidation numbers. Let me point out that we can assign the oxidation number for any atom in the formula, for any atom that we have. So the oxidation numbers, it's assigned at the atom level. It's not simply an entire compound has a number, it's at the atom level that we have within the formulas itself. Now, the assigning of oxidation numbers, when the book says it's just a bookkeeping one, it's not saying this literally takes place like this. It's just saying this is a way we can think about where the electron would be if it couldn't be shared, if it had to be on either one atom or another. Now, to give you sort of an analogy here, I'm going to take us to tacos. So think for a second. Are you someone that likes tacos, really likes tacos, or really, really, really likes tacos? I'm not going to even do this as a polling question. You notice I don't include don't like tacos because everybody likes tacos, okay? So take a second, think about, are you someone who likes tacos, really likes tacos, or really, really, really like tacos? Me, I'm probably in the middle category. I probably really like tacos. Anyways, let's say I grabbed some pictures off the web, okay? This little girl right here, she likes tacos. This baby really likes tacos. And this guy, he really, really, really likes tacos, okay? So in this analogy right here, you can't share the taco. Whoever likes it the most is gonna take it from someone else. So if I combine this girl who likes tacos and this guy who really, really, really likes tacos, sorry, he's going to take the taco. He's not going to share it. Okay. How about if he's compared with this infant right here? Sorry, he's going to take her taco too because he likes it the most. What about these two? The infant's going to take it because she likes it more. Okay. So my point is they all like tacos, but it's the degree. Who likes it more than another person? So if I were to now take this away from tacos, in this analogy, the taco is obviously an electron. Everyone likes a taco, and every atom, the electrons are attached to it. Okay? Opposites attract. The electrons are attached to the atoms. But when the atoms now are bonded to other atoms, what if you can't have the electrons right there being shared? If instead you got to like steal the taco, you got to steal the electron, where does it go to? Well, you need to make comparisons. And that's why I brought up that idea of electronegativity. It allows us to make some comparisons. Now, within here, one question, when we're assigning these oxidation numbers, will we ever have an example where the electron just stays with the atom that it's at? I just said we need to consider what it is sharing with. The only time that you don't worry about sharing is when it's with itself, because you like the taco the same amount. So the only time that we would have an oxidation number of 0, which means it hasn't gained or lost electrons, is when it's only just with itself. Other than that, when it's in a compound and it's with a different atom, we then say, where are the electrons found? So this idea of an atom being in its elemental form, that means the only other atoms that you have present are the same type. That would be an example now where the oxidation number would be 0. The only time it's 0 is when it's only with other atoms just like itself. When it's only with other things just like itself that like the taco the same amount. So when we're looking at this example here of assigning oxidation numbers, the question is, which cases would we have oxidation numbers of 0? It's going to be when we have the elements and they're all by themselves. It could be in a diatomic molecule like O2. Sulfur is in these rings that are this an eight member ring, or iron when I have iron solid, piece of iron all by itself. So assigning oxidation numbers when you only have the element by itself, that's easy. In those cases, the examples are 0. Another one I think that's pretty easy is when you have monatomic ions. We've already been looking at the periodic table and seen the columns that different elements are in and assigning them a charge. Our alkalis were +1, alkaline earth +2, aluminum +3, sulfur -2. Those, when we assign those for the atoms themselves, those are their oxidation numbers. So that's pretty easy to do as well. So we have some insights now for beginning to assign the oxidation number of sulfur. So if I look at it in an ionic compound, such as the strontium sulfide, strontium is in my +2 column. I sort of truncated it. It's down below there. It's an alkaline earth. Sulfide then would be 2-. So in that case, I can assign the oxidation number for sulfur when it's just existing as a monatomic ion. So we're partway to answering our question here. Now, if we look at the nonmetals, we have to be a little bit more clever. A little bit more is going on here. So within here, first of all, where are the nonmetals? Right-hand side of the periodic table, and hydrogen as well. Those are examples of nonmetals. When we're assigning the oxidation numbers within these, so first of all, let's jump down to fluorine. We said that fluorine is the most electronegative. It's always going to become negative. It will always become -1. So when I'm assigning for the fluorine right there, it's easy. It's always negative. It's always -1 when it's found in compounds. It's the most electronegative. The next most electronegative are the atoms immediately to its left and immediately below it, because that was our trend. Remember, it got more and more electronegative as it moved towards the fluorine. So the second tier of the most electronegative are oxygen and chlorine. That's why oxygen is almost always 2-. It's 2- when it's in ionic compounds, and it's 2- when it's in almost every molecular one as well, because it's the second most electronegative that I have. Now, if I compare that then with carbon, which of these would be more electronegative? Oxygen is more electronegative than carbon. Oxygen will become 2-. What is carbon then? Well, it depends on what the formula is that I'm trying to deal with. So take a second. What would you say the oxidation number is of carbon if I'm looking at carbon monoxide? Or if I'm looking at carbon and carbon dioxide? In both cases, the overall charge of the molecule is 0. They're both neutral molecules. In both cases, I think I know how to assign oxygen. And from that, I'll deduce what it is for carbon. See if you can do that. My analysis within here, I got to start with the part that I know. And the part that I know is the values for oxygen. Oxygen is more electronegative than carbon. It's going to become -2. So in carbon monoxide, the carbon must be +2. The whole thing adds up to 0. How about in carbon dioxide? Each of the oxygen again is -2, but I've got 2 of them, so the carbon now must be +4. My strategy for this is I got to start with the thing that I'm most certain on, and then from there, I figure out the remaining one. In this case, I am most certain on the value for oxygen. After I make my decision there, then I'm moving on to the one that is more variable, and that was the value for carbon. Now, if I'm looking here for hydrogen, hydrogen, based on its electronegativity, it turns out, even though it's way over there on the left-hand side of the periodic table, based on electronegativity, it's a little bit left of carbon. So when I'm trying to figure out what its oxidation number would be relative to the other ones, it's not as electronegative as my other examples of elements that I find amongst the nonmetals. So that's why it says within this one, hydrogen usually becomes +1 when it's bonded to the nonmetals, because that's consistent with it not being as electronegative. So something like an H2O, the oxygen would be the 2-, and the hydrogen I would be assigning as +1. If I look within these examples right here, let's step through these. So first of all, if I'm looking at hydrogen in NH3, nitrogen is more electronegative. Hydrogen would be placed a little bit to the left of carbon. So nitrogen becomes -3, and each hydrogen becomes +1. If I'm looking at it in lithium hydride, now I'm looking at an ionic compound. Lithium is in the +1 column, and I'd say hydrogen now is -1. It's been found in an ionic compound. In the water, in the H2O, each of the oxygens is +1 because the oxygen is -2, so each of the hydrogen is +1. The only one that I have left within here, it fits this category of a major exception. The major exception is something like this, when you have it in H2O2. Now, hydrogen only has 1 electron. It can only become +1 or -1 in our examples right here. So within this example, oxygen can't be 2-, because that would be saying that hydrogen had to be, each hydrogen had to be +2. It can't do that. It's only got 1 electron. So this leads us to this example right here, where this would be one of the rare cases where the oxidation number for oxygen is only -1 instead of -2. Now, this is, I think, the most, about the only exception you're going to see, H2O2, where oxygen is not 2-. Now, H2O2, it's not a crazy, wild substance, okay? It's this example of an exception for oxygen, and it's probably in your medicine cabinet at home, okay? Hydrogen peroxide is the name for it. So this would be one of the rare examples, though, when we're assigning the oxidation number for oxygen and it's not -2. When you add up the oxidation numbers for everything within either the neutral molecule or within a polyatomic, it gives you the overall charge. So in a neutral one, it adds up to 0. But what about in a polyatomic like this? What about within nitrate? My analysis here is the overall charge has to be -1. Oxygen is more electronegative. Each oxygen is going to be -2. So I use that and I solve for nitrogen last because the whole thing has to be -1. This idea of looking at a polyatomic and knowing the features that you know most solidly and moving to the ones that might be variable, that's how many of the oxidation assignments take place. So to step through then here, the sample exercise. So this is a sample exercise, and I really like the explanations that are given within the book on this. So I like it because it gives me a whole range of examples for sulfur. And if we were to work these through, I think the authors have done a good job of choosing different things to illustrate and discuss. In the first example, in H2S, we have an example where it's being found in a molecule, and the sulfur is the more electronegative, so it becomes -2 in this example. We have an elemental form where it's 0. We have an example where it's now found once again in a molecule. And if I were to say, well, what becomes negative, the sulfur or the chlorine? Remember, my second most electronegative are the oxygen and the chlorine. So the chlorine one is the one that becomes negative. So in this case, sulfur becomes +2. When I'm looking at, in example D, and I know I'm going quickly through here, these are all examples that are discussed within the book here. The book gives you a longer explanation on this. My recognition on that is this sure looks like an ionic compound. I know that the sodiums are going to each be +1. I know the oxygen will be -2. So I use that to solve for, at the end, I'm leaving the sulfur for last in order to determine it. In my last example for a polyatomic with sulfate, in sulfate, the overall charge is 2-. Each oxygen is 2-, and I've got 4 of them. So the sulfur itself must be +6. That's my problem solving approach as I work through all of these. Now, I'll point out within this, you can really see how this could set up easily for a multiple choice format on a test. It's really easy to list different examples and ask something like, okay, in which of these compounds is sulfur the most negative oxidation number? or the most positive or whatever. So it's really easy to ask a question where you have to do multiple assignments and then analyze it that way. Now, if I look in the chapter, a couple different examples, if you want to practice them later, in each of these ones, the nature of the question's pretty easy to predict. It's asking for the oxidation number. It might be for a particular atom within it, or I would argue you should be able to assign the oxidation number for all of the atoms. One hint, one suggestion as far as what to practice within here, this would be the most difficult. Make sure when you're practicing oxidation numbers, you practice some molecular compounds too. Students usually have a lot better success when they're assigning oxidation numbers in ionic compounds than they do in molecular ones. So make sure you practice some molecular ones too. Now, we end up using oxidation numbers when we move on to the next part, which are looking at redox reactions. So this would be an example then of a redox reaction. How do I know that? Well, if I assign the oxidation numbers here, I see that elemental calcium started as 0, elemental oxygen started at 0, but in the ionic compound now, calcium is +2 and the oxygen is -2. I see that the oxidation numbers have changed. We assign oxidation numbers in order to track through these particular changes. So I find that if I'm adding electrons, I'm reducing the oxidation number. So in this case, the O2, the oxygen in that was being reduced because it goes from 0 to -2. I'm adding electrons. Reduction is gaining electrons. The calcium is being oxidized. So in order to determine what species was oxidized and what was reduced and whether this is a redox reaction at all, our first step is we have to assign the oxidation numbers. And then we have to apply this terminology. Oxidation is losing electrons, reduction is gaining. Let me work through a couple examples. So within this case, the question is which element is oxidized and which is reduced? So it's showing what happens at the particle level. It shows in a formula and it shows what's taking place within the test tube. You take a piece of calcium solid, you put it into the silver nitrate solution. Notice it said silver nitrate aqueous. Silver nitrate aqueous, let's think back. Ionic compound, it's broken apart into the silver plus, the polyatomic nitrate. That's what's floating in the beaker initially. And a redox reaction takes place. What you find is forming on the surface now is silver solid, and you have calcium nitrate, copper nitrate floating in the beaker. So in order to confirm this is a redox reaction, I would assign the oxidation numbers. Copper solid is 0. Silver solid is 0. Those are the elemental forms. In the silver nitrate, the silver is +1. In the copper nitrate, the copper is +2. I see the same polyatomic on each side. I see nitrate on one side, nitrate on the other. If it's the same grouping, it's not going to change its oxidation number. It's the same grouping. I could go ahead and assign nitrogen and oxygen in those, but they're not changing. It's the same grouping on both parts. So that won't be involved in changing its oxidation number. In this case, I see that the silver is being reduced. I start with silver plus. I'm adding an electron and taking it from +1 to 0. The silver is reduced as an electron was being added to it. The silver plus is being reduced. The copper metal is being oxidized. When I'm applying those terms right here, which element is oxidized, which is reduced, we're referring to the specific atoms, and we want to look at the reactants for those. Yes, we want to do a comparison from the reactants to the products, but when we talk about the element being reduced, the element being oxidized, we're talking about them when they were reactants. So in this case, I think the silver plus is being reduced as it gains an electron, and the copper solid is being oxidized as it loses the electrons. So here's some end of chapter questions on this. They illustrate a few different ways that we can look at this. Notice the format. Which element is oxidized and which is reduced in the following reactions? So the first step for this, it has to be assigning the oxidation numbers. So let's look at example A here. Take a second. Let's see if we can assign the oxidation numbers. I see both N2 and H2. Those would be the elemental forms. Nitrogen atoms just by themselves is 0. Hydrogen atoms just by themselves is 0. When I look within NH3, let's think that through. Nitrogen is more electronegative. Nitrogen will become negative. It ends up being -3, and each of the hydrogens become +1. Now I have a change. They started out in as 0 in both cases, but the nitrogen has become -3, and each of the hydrogens have become +1. The nitrogen was reduced. I added electrons to go from 0 to -3. The hydrogen was oxidized. I removed electrons and they became more positive. So in order to go through the scheme here of identifying what's oxidized, what's reduced, we first start by assigning the oxidation numbers. Take a second, see if you can do example C for me. See if you can assign the oxidation numbers in C and determine what was being oxidized and what is being reduced. Skip down to C for me. So when I look down within C, it's going to begin by assigning the oxidation numbers. We'll look for changes, and then we can apply the terms oxidized and reduced. So if I'm looking within C, I see CO2, sodium iodide. I think each of the chlorine that I have is initially 0 in the CO2 because that's the elemental form. In the sodium iodide, sodium is in my +1 column, iodide's in my -1, so it's an ionic compound where it's +1 and -1. When I then look over at the products, I2, I'm sorry about the font there, that I looks like I don't know, a stick or something. I would say in I2, it now has a value of 0 because it's in its elemental form. Sodium is +1 and the chloride is -1 in the ionic compound. So if I look as far as what's changing, I see that the Cl goes from 0 to -1. It's being reduced. I'm adding electrons to that. It looks like the sodium stays +1 in both cases, but if something's being reduced, something else must be oxidized, and that was the iodine. It went from -1 to 0. Okay, now I can go on, but help me out right here. As we've worked through a couple examples, what's your current view right now as far as your self-appraisal when it comes to identifying which elements oxidize and which ones reduced? I think these different skills you need to have. You need to recognize the question format. You need to be able to assign oxidation numbers. And from oxidation numbers, you need to be able to apply terms like oxidized and reduced. So I think all of these are skills that you need to have. Which ones right now do you think you have? Can you recognize a question based on its format? Can you apply oxidation numbers, assign them properly? And if you know the oxidation numbers, can you apply the terms? Take about 10 more seconds. Okay, this is where folks come down on this one. Um, I like that we have a high proportion of folks saying that you're able to recognize the question. When we write questions on this, it's almost always this format. I mean, there's not much variation on it. It's very straightforward. There'll be different equations, different reactions, and it will just ask straight out, well, tell me what's being oxidized, what's being reduced. When it comes to then the actual strategy to solve it though, absolutely the first step is we have to be able to assign the oxidation numbers. And then once we assign the oxidation numbers, we have to be able to then apply the language of, is it oxidized if it's reduced? If I'm reading this question and I'm taking a test right here, when it says which element is oxidized, which is reduced, I'm probably pausing it. I'm probably writing oil rig. I want to have that right there and recognize that this is going to be my mnemonic that I'm going to use once I assign the oxidation numbers. Then what I'm going to do is I'm going to be saying, okay, do I have a strategy that always works for assigning the oxidation numbers? And I think the one that I've been trying to illustrate for you, I think it always will work. Let's work through one more example here. This is, I think, the most far-reaching within the set. Within this one, this would be a case that I know would be the lowest scoring. It's the lowest scoring for several reasons. Well, first of all, notice I don't have anything that's in its elemental form. It's going to make me work to assign in every example right here. So let me work that through. So this is asking me to do the most assigning. So first of all, if I have lead sulfide, ionic compound, sulfur becomes sulfide 2-, so the lead is +2. That would be how I would assign in lead sulfide. Hydrogen peroxide, wait a minute, this is the one that I got to be careful with. This is one where oxygen is not -2. This is this is an exception that we want to be aware of. Hydrogen is +1, oxygen is -1. So right there, I think that would be a little bit tricky, but I think we can accomplish the task. When I look within the products over here, in the lead sulfate, lead is +2. If I look in the overall sulfate, oxygen is -2, so that makes sulfur +6. And then the quickest one probably is in the H2O, hydrogen's +1, oxygen's a -2. Once I have all this, I think we can then do the assignment. That ones that oxidized lost the electrons. It became more positive. Looks like that took place with sulfur. It started out as -2, became +6, it was being oxidized. If I look now closely, something must be reduced. The only one that I see changing right here, it looks like I have oxygen go from -1 to -2. That would be how I would do my analysis there. So I think this oxygen atom is being reduced. This last one right here, I'll be honest with you, that's more likely what I'd expect on a test, okay? I don't expect like example A. I expect something where you're being asked to look at all the different features. So I think this last example, fairly representative for where I think we want to be able to get on an exam. Now, one more idea within here. We've talked about oxidation numbers. What does it mean to now identify what's reduced and oxidized? One last skill that I want to make sure we have some time to practice here. Within this last one, this was the example that we saw. So we saw how you can add copper solid to silver nitrate. An redox reaction takes place where you form silver solid and you then have copper nitrate. If you go into the lab here, and let's say you start instead by a piece of silver and you put it in copper nitrate. If you start with those, nothing happens. My point being that a redox reaction, if it takes place in one direction, the opposite doesn't take place. A redox reaction has a directionality to it. If you add copper to silver nitrate, a redox reaction takes place. If you start with the products and say, well, let me just run it backwards, it's not going to spontaneously run backwards. So our last skill is we want to be able to predict whether a redox reaction will take place or not. And in order to predict that, we're going to use some provided information. We're going to use provided information, which is called the activity series. So let me talk you through the data. Since it's going to be provided, let me show you how you can use this and it will always lead you to the right answer. Okay, we just need to understand how to manipulate this table. So first of all, Everything that's written on the table, they're all written as oxidation reactions. In every case, they're saying that it goes from the reactant to the product and it's losing electrons. Everything in the table is written as oxidations. Second thought is they're almost all metals that I see here. The only example that I have that's not a metal is this one that they've color coded differently for hydrogen. Everything else in the table is showing me a metal being oxidized. That's the first thing I want to be aware of. And that's what this arrow is showing. Ease of oxidation. The ones at the top here, these are metals that are very easily oxidized. We've talked about gaining and losing electrons. It's like a tug of war over tacos, right? It has to be transferred. It's like, who wants the taco the most? Who wants the electron the most? The ones at the top right here, it's easy to remove an electron from. The ones at the bottom, they're more readily to go from the ions to the metal itself. The ions at the bottom are easily reduced. It's easily to look at them as going from the ions of adding an electron to become the metal. The ones at the top are easy to form ions. So at the top here, these are typically forming ions, and the ones at the bottom are typically forming the metal itself. Now, if you're to make sense of that, look at the things that are at the bottom here. I see gold, I see platinum, I see silver. These are all precious metals. Okay? These are all metals that I think that if you find in your everyday world, they are as the solid metal. I don't think you've ever seen gold ions, but I bet you've seen a piece of gold before, gold solid. Same thing with silver. If you have silver jewelry, you're experiencing the silver as the solid. My point being, the things at the bottom, they exist as the elements themselves. The ones at the top, something like lithium, I don't think you've ever seen a piece of lithium solid before, but you may have seen a salt that included lithium ions or sodium. Unless you're in a chemistry lab, you've probably never seen a piece of sodium solid, but you've seen sodium ions many times within table salt. So my point is that it's all relative. The things at the top easily become ions, and the things at the bottom easily become the elemental form. So let's see how this now is something that we can use to predict reactions. We saw that when we take copper solid and react it with silver nitrate, a redox reaction takes place. The reason that that is consistent with the table, the copper solid was oxidized and became copper 2+, because there was an ion below it on the table of the activity series that could go from the ion to the solid. The activity series, we always are going to have that switch takes place. The species above it, if it can be oxidized because you have ions below it that can be reduced, then the reaction takes place. That's consistent here with what we just saw in this example. Let me work through a couple examples to show you how we can use the table. It's provided as supplemental information, so let's make sure we're comfortable with being able to use it. Let's look at this first example right here. So the question usually is, does the reaction take place or not? Lithium solid and calcium 2+. I'm going to find them on the table. Lithium solid, calcium 2+. Would a redox reaction take place? I need that the species above go from the solid to the ion. If there's an ion below that can react to go from the ion to the solid, that's exactly what I have in this case. So in this case, that redox reaction takes place. The solid above it becomes the ion because there's an ion below it that can become the solid. An oxidation and a reduction. How about this combination right here? What if I start out with lithium ions and calcium ions? I don't have a solid that can be oxidized when the ions reduce. They're both already ions. So there's no reaction that takes place then. So the typical question would be, it tells you the species that are there and it asks, does a reaction take place or not? The first one did, the second one doesn't. Let's see how we'd interpret these next two. Sodium nitrate and silver solid, silver nitrate and sodium solid. I just gave you both different options there. Take a second, look at the table. One of these reactions is going to take place and the other one won't. Look at their placement on the periodic table. Which of these do you think takes place and which one won't? As I look at these, I need to find their placement on the activity series with the provided data. I think that the first one will not take place. What is my comparison? I am looking at silver solid, and I'm comparing that with sodium ions. Silver solid and sodium ions way up here. Silver solid, I see silver solid all the time. I rarely see the silver ions. It's favored to become the solid, and it already is the solid. There's no reaction if I'm combining the solid with an ion that's above it. So the opposite is taking place. The opposite does occur then. If I combine the sodium solid with an ion below it, the sodium solid can be oxidized, while the one below it can be reduced. Again, in each of these, that's the analysis that I'm looking for. I'm looking for the one that's higher on the table to go from the solid to the ion, while the one below it is reduced and goes from the ion back the other way. So within here, this is a typical format for the question. So here at the top, I show end of chapter question where it gives different reactions. It says, use the activity series, write balanced equations for these. And if no reaction occurs, write NR. That's our symbol for no reaction. So give me a real quick check-in right here. Let me send you a polling question on this. Where do you come down right now on activity series? Is it something where, can you recognize the question format? Are you able to see if a reaction occurs? Are you able to see if a reaction does not occur? What's your perspective right now? I think folks are doing a really good job of saying that you can recognize the problem. Almost every time within these, it will say using the activity series, but I think that you're going to be able to even develop the skill where it won't say using the activity series. You're going to be able to interpret these and determine, yeah, I think that they're talking about redox reactions or not. This idea of can you use it though to see if a reaction occurs or not? I think we still need to practice that. Let me give you another one, okay? So this one they're asking, aluminum metal is added to cobalt sulfate. Does a redox reaction occur? We need to find aluminum metal on the table and we need to find the cobalt ions. Aluminum metal, cobalt ions. What are your thoughts? I see the metal above the ions within here. I think it will occur. I think the aluminum is going to be oxidized because there are ions below it that can be reduced. That's how I'm using the activity series information. In this case, it's asking for a balanced chemical equation. I would first determine whether a reaction occurs, and then I would write down what the species are. Aluminum metal is reacting with cobalt sulfate, to form cobalt solid and the aluminum sulfate, and I could balance it from there. I know within here the real challenge for you is, well, how do you interpret the information in the table in the first part? Let me give you another try on that, okay? I think we're getting better on it. So how about this one? Does a reaction occur when aluminum metal is combined with, and I give a lot of different options. Let me show you where these are on the table. Okay, so I've circled 1, 2, 3, 4, 5, 6 different things. Take a second, look at these. Based on the placement of aluminum, what would it react with? So when I'm looking for this to see whether it reacts or not, I'm saying that the metal would react if I have ions below it on the table. I see three different examples of that. I see that it could react with silver ions. I could see how it would react with H plus, or it could react with zinc 2 plus. When it comes to using the activity series, as a teacher, I find it's difficult for me to teach this because I already know the answer. I know exactly how we use this table. So I find that it's really difficult for me to try to help support you as you're trying to catch up to me because I'm not that far ahead of you. I just know what does it mean to say it reacts or not. But I do think as I've tried to teach this in different ways, I think might be, at least with me, I think this is the most persuasive. Meaning, if I look within the example, what would aluminum react with? Any of these ions that are below it. I think all of these are examples that the aluminum is going to become oxidized and these other species are going to become reduced because they are ions below it on the activity series table. Now, we're almost done. Great job sticking with me. One thing within here, I want to draw your attention to this H plus part. We're going to see in our next class when we look at acids, how acids give us H plus aqueous in the solution. That's why it's showing up in this table. So everything else within the table here, they're all different metals and ions. The only thing that they've added to it is, oh, well, an acid might also be relevant. That's why it's listing the acid being present here too. And in fact, that's why one of these choices right here, it's a little bit more advanced for us, but we're developing that idea where it says, would hydrobromic acid give you a reaction when you add it to tin metal? What it's really saying is when you have hydrobromic acid, oh, that's a source of H plus. We'll look at that a little bit more when we look at some behavior of acids and bases next time. But I'm just pointing out that's why it's showing up on the table. So if I have some suggested end of chapter problems on this, both of these are directing you to the table. They're both saying use the activity series, table 4.5, find the different things on the table and determine whether a redox reaction takes place. So here's another set of skills that you can practice. Now, what I want to close with right here, I'm going to be able to provide you better context in our next class about everybody's exam performance and stuff. We're still working through some of the data. Some people still have makeup tests to take and stuff, but I can provide some greater detail on class on Thursday. One thing though, people have been reaching out to me and turns out I have a computer program that I have access to, a computer system that allows me to deliver to students my own questions. It's not in mastering, it's my own questions that I can write. And sometimes I've used that as optional assignments for students, not for credit, but just to help students develop what I would say the essential skills they need to solve more complex problems. Think about all the things that we've been doing. Many of the ones involving stoichiometry first begin by understanding a proportion. We began naming some compounds and then we did a lot with that. We used a periodic table as a simple skill and then we did a lot with that. We assigned oxidation numbers, and now we're doing a lot with that. I would argue for all of these, the more complex problems begin by mastering these essential skills that we then put together and that we can then use to solve for more complex problems. So within this one, it's a resource that I can share with you. I've got to work a little bit harder to prepare it, but I can do so. Send me your perspective on this. If I make this, would you be willing to give it a try? It's going to be an optional one. They're going to be small, very low stake sort of check-ins. But I've got data. I know that it can be effective. Share with me your perspective if you'd like to give it a try. And the reason I'm gaining your perspective on this, I know there's a lot of resources in the course already. You're doing a great job contributing to perusal, mastering chemistry. You're coming to class, you're doing a lot of things already, but I'm just trying to make it so you're not overwhelmed, but you've got as many resources as you can to be successful. So as I look within the results right here, general consensus is, yeah, it might be something that you'd at least give a try to. And again, this will be something that is no pressure at all. Let me put it together and I'll share details with you on Thursday. I think it will give you some repetition and some practice on what I know are important skills that you need to build up. Uh, it won't be for a grade, won't be for anything but your own benefit, but I think it will be helpful. So this is another thing. Let me put that together and I'll share details with you on Thursday. And as always, folks, I really appreciate your attention. I'll hang around if you got questions.
I was just wondering, for the ones that are asking us whether a reaction takes place, do you think if we encounter questions like that, there'll always be one of the reactants is just as in its elemental form?
Uh, when we're using the activity series,
Yeah.
I think within our activity series, as I look at it, in order for there to be a reaction, I have to have at least one of them in their elemental form. Then, as you know, I'd have to look more closely and see what could it react with. But I think in my examples, if I only see ions present, I'm not going to have a redox reaction.
Okay.
I have a question.
Mhm.
So when does the sum of the oxidized numbers not equal zero? Because I know in some of the examples it should equal one. When is it not supposed to equal
Yeah,
zero?
yeah. So the when I was doing assignments, like, well, here's one where you see a whole bunch, but let me just go to something like this example right here. So in this case right here, when I was trying to identify what was being oxidized or reduced, I was assigning for the particular atoms. Now, if we wanted to step back and say, should the overall charge also not mean that I'm gaining or losing? Notice within here, I've got a silver that's +1 and another silver that's +1. So the overall positive charge would be +1 and another +1 or +2. That's why the overall charge is indeed staying the same if I compare the reactants and the products. I just wasn't listing both of the silver there. Is that what you're saying?
I think so. So when we have a coefficient in front of the terms, the sum isn't going to be zero.
If you have the coefficient within here, I would write this more if I wanted to put in that. I have a +1 and I have another +1 because I have two silver atoms there. That makes it so I can see that the overall charge is +2 on the left side and +2 on the right side. The overall charge is going to stay the same before and after. Another way of saying it, the charge will be balanced. But when I'm trying to determine what's oxidized or reduced, I don't really care about the overall charge. It's going to work out if I'm careful within that. It's going to work out, but I'm more interested in determining what was the oxidation number for the given atoms, because that's what I'm looking at to see if it changes or not.
Okay. Thank you.
I guess what I'm saying is that when you're looking to assign the oxidation numbers, do not worry about the coefficient.
Okay. Yeah, that's what I was confused about. Okay. Thank you very much.
Yep.
For the question with lead sulfide, so when you have two elements in a compound that both have, like, I guess, changing oxidation numbers, should you just assume the one that has a more consistent oxidation number. I don't know if that made sense.
Well, I got the data up here. What part are you looking at specifically?
So with lead and sulfur,
Mhm.
well, first, I guess my first question is lead always +2?
Uh, I
Or is
know a
that
little chemistry. No, it's tough for me not to feel like, well, you asked me something that I actually know, so I can tell you lead's usually +2 or +4. But
okay?
in our case, but I would say as a student, if I'm trying to solve this, I would say, okay, this appears to be an ionic compound.
Mhm.
If I'm assigning, I'm pretty confident that sulfur would be in my 2- column. So if I were you solving that, I probably would have started by saying sulfide is -2.
Okay, so like I don't know if this would like be a rule you could use, but could you say like the one that is more commonly something, assume that one and then go off of that?
Yeah, and are you thinking more for ionic compounds, or are you thinking for when we're looking at molecular ones?
Ionic compounds.
Yeah, I think within the ionic compound, you might be, I agree with you, but you might also be working a little bit too hard, because if you see
Mhm.
the PBS, you know whatever the charges have to be the same because it's a 1-to-1, right?
Yeah.
And so within here, um, I, I don't think you'll go wrong. I think within here, um, within my reasoning, I've only seen sulfur as -2 in my ionic compounds. So I would sort of be saying, oh, so therefore it must be lead 2+.
Okay.
But I think I'm agreeing with your. I don't think you're ever going to have an ionic compound one where it gets where that's the point, and they're not going to say, aha, that was lead +4, so this is sulfur minus or -4. I don't think you'd ever have that. That doesn't make sense.
Got it. And same with like where manganese can have like a bazillion different charges, like they would tell you that it was whatever
Yeah,
charge, or you would have one that you could assume.
yeah. I think with something like that, they'd have to like tell you more, like maybe if they gave the name with the Roman numeral or they designated it something like that. I
Okay.
think that I know that the main one on this one, if the question wants to be more challenging, we include molecular ones, because students get
Okay.
a lot, they have much higher success rate when it's ionic compounds than when it's molecular.
Got it. Okay. Awesome. Thank you.
Yep.
Does how do we know if the O2 is that just in hydrogen peroxide that the charge is -1, or is any compound with O2 the oxygen has an
Well,
oxidation
I
of 18?
noticed there was a in one of the end of chapter ones here, they had another example. Let's see if it's in, was it within a previous group? I mean, here would be another example.
Okay.
K2O2. So this is the potassium with the peroxide there. So this would be another example. Almost always the only time I see it is in the hydrogen peroxide, but that's what I know they're trying to allude to here, where the potassium's +1 and the oxygen would be -1.
Okay, so also in like 4.5a, is it anytime we see O2, it's always going to be.
Oh, okay. I would say if I'm looking at it within this one, that's a good question. I would say within here, I would say each of my oxygens is probably -2. So that would be -2, -4. Yeah, I think it's probably within here. Like I am almost always going to make it -2.
Mhm.
If you notice the times when it's not -2 and it's only -1 is when it's paired with other things where it's just it can't become -2. H2O2 is my best example because the hydrogen can only become +1. So the oxygen can only become -1. And that's what we're also seeing here, that my potassium's being +1, so the oxygen becomes -1. But in all of these other examples, I'm not going to be fooled and say, oh, there's an O2. In all of these other examples, I'm going to be making it as the oxygen itself will be -2.
Okay, and that's the reason that potassium is like that is because it's it only has one electron in its valence
Yes.
electron shell.
Yep.
Okay.
I just had a question not directly related to the to today's content, so I just want to wait till everybody else was
Okay.
done asking their questions. But I wasn't